All right, we'll go through thermodynamic processes. So this was just the meeting for today, and if you missed, it's important that you go through the video. All right, at end time. Okay, so we are talking about thermodynamics processes. We'll talk about the processes and just some derivatives and also some a bit of examples. All right, so there will be part one and part two of today's lecture. Okay. So, since we are to talk about thermodynamic processes, all right. So, suppose now we are studying heat, by the way, and in us studying heat, there are there will be processes which will be changing. All right. So, the change in temperature, all right, when just temperature is actually changing, we call that as the isothermal process. All right. So we call that as isothermal. Okay. So isothermal process, it will be just a change that will be taking place due to temperature. And this by this temperature will be constant. All right. So it can be, let's say a heat is released and also being absorbed at the same time. So it will be always at the equilibrium. By this, we mean temperature now will be what? Constant. And when temperature is constant, meaning that even the dy or just the dt, all right, the derivative of that temperature will be zero. All right. So heat will be released or absorbed in this change, but just know that a constant will be always maintained. So temperature will be maintained. All right. So then the work that you are going to find under isothermal process will be also equal to what? To the temperature or just to the heat that is being transferred or being absorbed. So in short, once this process is maintained, so temperature at this point is constant, meaning that it can be absorbed or released, but the equilibrium will be always set. All right. So there is what we call a process called a adiabatic process. So adiabatic, when you hear something like adiabatic, all right. So the moment you hear the word adiabatic, just know that it's relating to what? To heat, and heat is always presented by Q, all right. So in this case, we are trying to keep heat constant. So meaning that the dq, all right, the dq or just a derivative of this heat of which we have as a constant, all right, will be zero. Always the derivative of a constant number will be what? Zero. All right. So that's about adiabatic process. Heat is being maintained by this. The process or just a system will try to reach the equilibrium. So suppose we have the system here, all right? Let's say a reaction. So this reaction now, heat can be given out, or again, heat can be what? Absorbed. So once the heat is given out and being absorbed at the same time, the process will reach at the equilibrium state. All right. And the process of having two things at the same time and of which they are equal in magnitude, we'll call it a adiabatic process. All right. So the next process that we are going to talk about is the isobaric process. So when you hear of isobaric, from the word barometer, something like that, okay? Isobaric process is actually the process that try to keep what? Temperature, I mean pressure constant. So meaning that the dp of a pressure or the derivative, the change in pressure will be always what? Zero. Because it will be either negative or positive, but with the same magnitude. Okay. So those are the things that we'll be looking at. So you can be asked what is isothermal process. So you give these conditions, then you'll be ready to go. So the other condition that we can talk or just the process is what we call isochoric process. All right. Isochloric process. What is this isochloric process? So isochloric, this one is relating to volume, and we are saying volume is constant at this point. So volume is being what? Maintained constant. So we'll say the dV, all right, or the derivative or the change in volume will be always zero. Since we have volume as constant number, it can again reduce or what? Expand, to say. So the volume will be changing just like that, and that's the reason why we're saying the div of this volume will be what? Will be always zero. Okay, so these are the processes that you can be asked sometimes in an exam, and it's important that you master some of the changes that take place, what is being maintained. So you can take in the form of just as if you are trying to what? To achieve the equilibrium, and you are, when you are achieving the equilibrium, the net change is always what? Zero. Okay, so from there, since we are now able to define these processes: isothermal, adiabatic, isobaric, and also isochronic. So since we're able to define these processes, now we can go to what we call path and state functions. All right. Okay. Okay. So what we are going to do is we are saying state and path functions. So we are going to understand what a path function and also a state function. All right. So a path function, to say, or let me start with a state function. So when you hear the word state function, all right, what type of a function is this? So a state function is actually is just a property of a system that does not depend on the series of steps taken to achieve that state. All right. So suppose we have, let's say, a mountain there. All right. So we are about to climb this mountain. We want to get on top here. This one is going to climb, then this one is going to jump into this mountain. All right. So under state function, we are not we don't care the path taken. What we want is just to reach what? That point of interest. So we are saying a state function does not depend on the path taken to reach that state. All right. That's about state function. Okay. Then there's what we call now path function. You can even hear the word is path. All right. So this one would depend on the path taken um, by the system to reach that state where it is. All right. Let's say it's a solid. So we'll talk about to solid. For it to be a solid, maybe it had to do what? To freeze, something like that. So that's about to path and also state function. All right. So the other one depends on the series of steps or just a step taken. Then the other one does not do that. So for state, you just consider where are you, like let's say mass, you just consider the amount which is there. All right, you're not talking about, let's say, if I give you a path, let's say speed. All right, speed is equal to what? You need to have distance and also time. There are things involved for you to have speed. That's the reason why we say path, meaning you are passing through something for you to reach that path or that state. All right, so that one which will be depending on the initial and final state of the system, um we actually call it as what? State function. You are just interested in the initial or just final position. All right, but for path, you consider all the things you have used for you to reach that process. All right, then suppose we have the state, let's say the state M there. All right, okay, then this state can undergo, let's say, process A, then again into process B, again into process C, again into process what? D. All right, like that. So we'll actually see how we get the state function and also the path function. So for us to get the path function, what you're going to say, I mean the state function, we want to prove the state function for this substance. Is it true that at this point is just the same thing as the final point at the initial? So what you're going to do is we'll actually come up with some equations. We'll say this is the system, by the way. These are the things involved in a reaction. So what you are going to do is we'll say a change in internal energy, all right? Change in internal energy, all right? Change in internal energy of what? A, all right, to B, all right, to C, all right, to D is equal to, all right? Um, there will be energy of B, all right? We just want the difference here. There will be a difference and also the difference there and also the difference there. You get? So there will be energy of B, all right, minus energy of what? A plus, all right, energy of what? C, no, this is C, all right, minus energy of what? B, okay, then plus we have energy of D, all right, minus energy of what? C. So it's just the difference here, the difference and the difference and the difference there. All right, so the difference 1, 2, 3. There are three differences. So we can see that B and this B will go, right? And again, we can see that C and C will go, right? D, no, there must be A somewhere here. All right, so D is not going, so D is positive. So I'll say the same D I'm from just lab. Let me just remove that. Okay, so the same D, so we have remained with A and also D. All right, so we'll have internal energy of D, all right, minus internal energy of what? A. So meaning that we can see now that this state M, all right, the energy required actually to reach to be of this state M is actually just the difference of what? D and D, which is the final minus what? Initial. All right. So hope that is clear. Okay. So let me give you another example so we can conclude. So take note of this one. Hope you have taken note of this one. You can write it down somewhere. All right. Write it down somewhere. Write it somewhere, please. Or let me just go to another page. Okay. So suppose now what you're going to do is um suppose now we have um again, let's drive something here. Okay. So the same change that we had M there, all right? So M had to undergo process A, all right, into process B, into process C, into process what? D. All right, like that. Okay. So what you can do here again is we can say that the change, all right, so this change can be, remember, from proving to this D, all right, all the process that we had between. Now we want to prove using this path, all right, A to D, all right. So what we are going to do is we're going to say change in internal energy, all right, using the path. Which path? We are using the path A to M, all right, to D, all right. So this is the path now that we are taking. Okay, so what I'm going to do here is that I'll say um change in internal energy of between A and M there, all right. There will be change between there, and also there will be change M and D, that between. So here I'll say this is A M, all right, plus the change again internal energy. So the change in internal energy of what? Of M and D, all right. So I'll say M and D like that. Okay. So this now will prove that the change between A and M there, you just, the difference. So we are starting with M as final initial. From this point, let's say you start at this point. Then for you to reach this point, you need to do what? To subtract the final one. So I'll say internal energy of M, all right, minus internal energy of what? A, all right, plus again internal energy of D. So internal energy of D, all right, minus the initial, which is M, the internal energy of what? M, like that. Okay. So we can see that um M and M goes, right? So this conclude that still, you see, the internal energy of D minus this one, the internal energy of what? A, change. So it's still giving us what? The same thing even if we do this path. Okay. So meaning that the first one we had, it was what? It was reading from the change in internal energy of a system using the path A to B to C. That was the first one. To D, all right, is equal to the way we actually came up using the other way around, from A, M, D, all right. So I'll say it will be equal to internal energy, or just change. Let me write change. So they must be change somewhere there. So there was change in internal energy. We moved from A, all right, M, D, all right, and it gave us what? Um, the change in internal energy between A and D, which is just equal to what? Internal energy of D, all right, minus internal energy of A. So this is one of the formula we can use because we have derived this formula, all right, and that's something good, that we have derived the formula. Okay. So now we'll go now to what we call cyclic process. Under this cyclic process, we'll see something here relating to to path and also state function. All right. Okay. So suppose we have, so let me say cyclic. So a cyclic process um, is a process that returns its initial state after a series of changes. After you change some things, a lot of things, let's say you apply this and this and this, you still go back to what? Your initial point. Let's say you had what? 1,000, all right? After spending, let's say you pray a bonanza, you buy other stuffs, you still again receive that money again. Let's say you receive money, all right? The same 100 kwacha, all right? That's what we call a state function. It will still return to the initial position. That's the meaning of um, um, cyclic process. So a cyclic process will always return to its, let's say, start here. It will actually go all the series and still come back at this point. And we can prove this, meaning that if it return at this point, it's just a different direction it can use. So we can have, let's say you go this side, you're going to the market, all right? You meet the market there. And also if you use this side, you meet the market. Let's say this is negative, this is positive, and when you add this, they will still give you 0. At this point, you still return to what? To your initial point. Let's say you started at 0, all right? So you go to the market, use 2 meters. Again, you reverse this side again, use what? Negative 2 meters. So you still what? You still come back to what? To 0, to your initial point. So that's the meaning of cyclic process. So a cyclic process will always produce what? Um, a cyclic process will always produce the magnitude of 0. Okay, the change in internal energy will be 0 for a cyclic process. All right, hope that is clear. So master that a cyclic process will behave like that. Okay, and we'll prove that. Let's say, suppose we have a board A reading into board B. All right, these are steps now C to D, like that. Okay, so now what will happen is that we'll say, want to prove this cyclic process, all right, that if it will still give us 0. So we are here to prove. So I'll say, since these are the changes or the processes that we are being taken, so um I'll say this is a system, by the way. So I'll say change in internal energy of the system moving from A to B to C to D like that will be equal to, all right, change between B and A. So I'll say change in internal energy of what? Between A and B plus again change in internal energy of what? B and C, all right, plus again change in internal energy of what? C and D like that. Okay, so hope that is clear. So what we are going to do from here is that we'll say between A and B we are subtracting this one minus this one, right? So is this minus this to find the change that is here, the change that is here, that is here. So we'll say this is now uh internal energy of B, all right, minus internal energy of what? A. Okay, plus, all right, internal energy of what? C. Okay, minus internal energy of what? B. Okay, then plus. Okay, now here what will happen is that we'll say internal energy for us to find um between C and D, all right, so we're going to say internal energy of D, all right, minus internal energy of what? C. Okay, hope that is clear. All right, so what you're going to do here is that there are things that will cancel out here. So, and again, we have to take, since it's a cyclic, again, I'll move to this point, right? So here there will be what? I'll have again plus. It's a cyclic. I'm making a circle, by the way, and in this circle, I'm trying to connect. I've moved already this side. So now I'm going back from D to A. So what I'm going to do here is that, again, in fact, I was supposed to add here to say there will be again the change in internal energy of what? Of A and D. So here what I'm going to say is that I'll say internal energy of what? A, because the final is position, minus internal energy of what? D. All right. So we can see that it's a cyclic process. So what I'm going to do is I can see B goes and also this B goes. Okay, then I have C positive there. All right, I have C negative there. I have negative A there, I have positive A there. All right, I have positive D there, I have negative D here, which will give me what? 0. Meaning that for a cyclic, always the change in energy or in the internal energy of the system is what? Is 0. So the function whose cyclic integral is equal to 0. Okay, so this um function whose integral is equal to 0 is same as even that of the differential. Okay, so differentiating is just to change a bit of it, so we have an exactly differential from this integral. So and by this we'll prove using a certain rule. So what I'm trying to say is the change, so this is a change in internal energy, all right, so is equal to 0. We have seen this. So a bit change of integral of this the same um um cyclic, all right, so I'll say DE like that. Okay, just to show the change in this, which will give me 0. All right, so this is the integral, right? And if a function obeys this, all right, to say the integral of this DE, by the way, is just change in energy, then is equal to 0. All right, so some functions will be obeying this, and those functions which will be having this and they are giving even the same differential as 0, all right, we'll actually call them as what? Cyclic processes. And since they are cyclic process, we'll be proving them by using what we call this guy, or just a theory called what? Euler's theory. All right, it's U then ERS like that. Euler's theory. So this Euler's theory is a guy who came up with something to say when there will be change, the change in we'll prove it to say the change in a cyclic process will be given by the formula. Let's suppose we have a function dz or just z, all right, which actually depends on x, a, y, and x like that. Okay, it's a function z. So for us to find the dy dx of this function, what we are going to do is we'll say um, we'll say dz, all right. I just want to remind you dz, this is complete derivative, so I'll derive a what, a bit, I'll differentiate a bit of x and keep y constant. So I'll say partial derivative of z, all right, over, now with reference, what am I differentiating? I'm differentiating a bit of x, all right, partial derivative of x, then I'll keep y constant, then this is now dx, then plus, all right, um again a partial derivative in z, which is the subject of the formula. I'm changing a bit of y now, all right, then by this I'll keep x the constant, then this will be dy, to mean dy is what, changing. Then from there, when these two things are equal, all right, when they are equal, let me show you something. When these two things are equal, this is about Euler's theory. So when these two things are equal, suppose this one, let me write this one as m, all right? Let this one be m, this one be n, all right? So I'll say dz, all right, is equal to m dx plus n dx like that, okay? I just want to differentiate them properly or just write them easily. So from there, since I'm able to have this, now when these two things are equal, all right? So I'll say Euler's theorem, it is actually a state function. It is trying to describe the state function. So when these two things are what, are giving this law to say the partial derivative, let's say in m, all right, with reference to what, to change in what, y, keeping x constant, then is equal to what, to the same thing that we have. I've just changed the direction opposite. So change in what, in n, then a bit change in what, x, then keeping what, y constant. So when this law is being obeyed, then a function is what we call what, a state function. Hope that is clear. Euler's theory is there to prove for what, a state function, and all these that I'm from proving are state function, which give me zero, meaning that they just depend at the same position. You get the point? No matter how step you have taken to reach that, them they just go direct on that position. Just say mass. Mass, you just say the amount of mass is this one. The amount of matter in that mass of the body is this one. So you don't talk about the speed, let's say the volume, everything like that, the density, stuffs like that. You don't talk about that. Okay. So that is it about Euler's theory. Is there to prove the for a state function, and when this law is obeyed, then a process is what, a state function. Okay. Hope that is clear. So now what we are going to do here is um I want to give you a series of state function, and I'll explain why they are like that. So there are a lot of systems or processes that will be looking in this stage. So one of them is let's go to a next page. We see something. Okay, so we are talking about state function and also path functions, right? But I'm from proving a lot of state function, and I hope it is now getting clear. I'm from just showing you that all the state function, they will come at that position. All right. So what I'm going to do is I'll say for a state function, let me write the same rule, Euler's theory. All right. So Euler's theory actually is giving us the formula, partial in m with change in what, in a bit of y, keeping x constant, all right, then is equal to the same thing, those things in the total derivative of z that we had, partial derivative of m n over partial derivative of what, x. Now keep holding what, y, they are constant. So from this, we can now conclude some partial, I mean state functions. So when you say state function, it only depends on what? One thing. So state functions. So one, pressure is one of the what? State function. Why? You just say pressure is what? Um, um, Pressure is a state function because you only give pressure as you just tell someone to say pressure is this one. Okay, we have a 1 atm. Okay, you just give the reading from the barometer. Okay, then we can also talk about the temperature. Temperature is also state function. So you can say temperature is 25 degrees, um 20 kelvins, negative something kelvins, everything like that. So is what? You just get one thing. It's a what? It's a state function. We can also talk about uh S being what? What is the abbreviation S in the thermodynamic study? Okay, S is entropy. Entropy is just the start of how the arrangement or particles are being arranged in a system. So that is entropy. How particles are scattered in a system. Let's say in a solid. That's what you call entropy. So you just go there to say the entropy is higher. All right, you are done. So meaning that you are not involving any calculation to say divide this by this. That's just a state function. Just go direct and point. Just like pressure. It's 1 atm. Okay. Then the other thing that we can talk of is the um what we call enthalpy. Now enthalpy is being presented by H. So this enthalpy now is also just a change. You just give the value, you just find it, especially when we start talking about um Hess's law, everything that in enthalpy will be what? Will be just the value, okay, the magnitude. So you just point to say this one. So that's one of the what? State function. Okay, so the other thing that we can have um is what we call now um internal energy using U. All right, so this is abbreviated as internal energy. So internal energy is also, you just get, you pick the internal energy which is there in the system, which is inside the system, then you are done. It's a state function. You are just at that point, at that state. Then we can also give this is Gibbs free energy, G. So Gibbs free energy is actually given by a certain formula to say entropy times temperature times what? Change in what? Enthalpy, something like that. So I'm just imagining to say it is actually the value only. But those things that are involved at the end is what we call. So, in short, for you to master this entropy and everything like that, let me just finish. So, Gibbs free energy, just know that is a state function. Then there's the Hamilton's free energy, which is presented by A, Hamilton's free energy. So, Hamilton's free energy is also a state function. Okay. So, by this, I mean, let me get Gibbs free energy. Let's say, or let me, which formula can I get? Let me just get the same pressure. Okay. Pressure we know is force per unit what? Area. Okay. Right? Meaning that you just get pressure there, you are done. But things that are involved are what we call state function, because you can see that force is what? And area. They are state function. This, I mean, they are path function in this case. But the less, this one is a state. You just get the state to say force is pressure is equal to this. You are just interested in the magnitude. And also Gibbs free energy will also be, let's say, change in what? Entropy plus minus change in temperature, something like that, change in what? Entropy. So I've just forgotten the formula, but I'm showing you to say these ones are what we call path functions, and this is what? A state function. Like you are just interested in that point. It's a subject of the formula to say. Okay. All right. Then let's talk about path functions as well. Okay. So path functions, what are these? Okay. So path functions, we can have best example. Suppose we have what? Heat. Okay. So heat will be what? A path function. And also wake will be what? A path function. Okay. So and also we can have what? Specific heat capacity, which is just C. So these are path function. Like for heat, okay. Um, let me give for wake or just heat. From wake formula, all right. Wake sometimes is equal to what? Or let me say change in internal energy is equals to what? Heat plus wake, like that. Okay. So you can see that heat is what? From this formula in total energy uh, in internal function, this formula U, all right, is equal to Q plus W. So this W is wake, right? That's the reason why we're saying wake is a what? Path function. Then and also heat is a path function. And also just this um um specific heat capacity is also what? A path function. So these they depend, they are just in a on a path, all right? Before the after the subject of the formula, we find them inside. So we call them path functions. Okay. Hope that is clear. Okay. So the same heat we are studying, this heat we are studying, it can be um this heat we are studying, it can be actually it's under the system, right? We are working with a system, let's say reaction. So heat, let's say this is a system, all right? We talked about the type of system, everything like that in the other videos. So what will happen that this system, it can expand, let's say a balloon, all right? Once it gives, it expand like that, it what? It is doing work. So the work there, which is giving us what? Um, um Negative, all right, because it's giving, when you're giving something, you have something like a negative, you'll be charged negative, all right. Then when again a work is just being done on a system, then we'll have work as what? Positive, all right. Here we'll have negative work because the system is the one which is doing work. Okay, so from there we can say that, let's say we have this is a jar, all right. Okay, so at this point we have a certain pressure, all right, pressure, or just the arrangement of this particle inside. We call it S1, entropy 1, then I'll call it entropy 2. All right. So what will happen that, let's say I put some stones there on top. All right. This thing is going to at least be compressed a bit so it will come at this level, right? So you need to know that even if the pressure, there's pressure there outside, all right? So there's pressure external, all right, and also pressure internal in the fluid to say. So what will happen is that if I put some stones on top there, all right, a compression process will take place a bit, right? And also, but just know that pressure is equal to external pressure is equal to what? Internal pressure, because it's just the same heat that has been observed is the same heat that will be what? Released, and the same pressure that has been what? um Made is the same pressure that has been applied. So for by that we will say pressure doesn't change in this system. Okay, it will be constant. So um we are saying when, now see what will happen. This is a balloon to say, when pressure in the what? External, outside there, is greater than the pressure which is inside, all right, this now will cause what we call compression. You're compressing this thing, sometimes it can even burst, so we'll call this as what? Compression. But the same P1, I mean P external, is just equal to what? P internal. They are equal, it's just that they are trying to reach the equilibrium. Once the equilibrium is reached in terms of the height they need to share, then the system will stop. Again, when this pressure external, all right, is less than the pressure what? Internal. This is what we call now what? Um, the system or the gas, let's say the balloon is going to what? Um, uh, is going to expand. So we call this as the expansion. All right. In this expansion, again, the same pressure in internal is equal to the same pressure what in external, because it's just the system or the difference that has been created, and a net um, charge will be achieved, which will be just as still again zero, which is the isobaric. Hope that is clear. All right. So the other thing that we can do here is um, we know that the same force that has been pushed downward after I had to put some stones, there's a force that has which was what going down. So I'll say this force which was going down is what is due to the mass that I applied and also the acceleration due to gravity, right? So that's the force we have there. That's how we find force, right? So we know that pressure, all right, is equals to force over area. So pressure force now is what mg, all right? Area is just area like that. Okay, then from there what you are going to do is um we know that work, all right, is equal to force times the distance. We know this even in physics we did in first year, all right, whereby this force will be at a certain angle. We remember this. So what will happen is that I'll replace um this force, okay, over what um I'll replace this is force I have, right, times the, okay, I want to say this is pressure, right? Okay, then let me do this so that you don't get confused here. Okay, let me start this. I just want to show you something interesting. So we have force is equals to work is equals to um work. In fact, it is negative always. Work, the way it gives is negative fd like that. So what I'm going to do is let's say it's a piston that moves, all right, down. All right, so the piston is moving down there. So we're calculating the work which will be done. All right, by the way, it will give what acceleration negative, so it will be negative like that, or just negative is always there maintained, so fd like that. Okay, so what you are going to do here is that um 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 let me lab here. So I want to do something interesting here. All right, so we are saying work is equal to negative force times distance. All right. So what I'm going to do is I'll say negative force, all right, over A, all right, times A. There's nothing I've changed here, times D. So this A and A can go, it's still 1, right? So I'm just trying to do something. We have distance measured in meters and also area measured in what? Meters squared. So that will give us volume. So I'll say negative force over what? A times, now this is the volume, right? Are we good? So then force over area we know is what? Is pressure. So negative pressure is equals to what? Change, there will be change in volume, so we'll call it dv. All right, hope that is clear. So therefore work is equals to what? Change in what? I mean negative pressure times change in what? Volume. Hope that is clear. Meaning that for a change in external, all right, outside, the pressure that is outside, the pressure that will be actually causing this system to actually compress or just expand, this is the pressure which is in charge, the external pressure. So what you're going to do is we'll say downward, causing the one which is going downward, all right, the downward work will be what? Negative. All right, the same pressure is the external pressure, all right, then times what? um Times the change in what? Volume. Okay, so this is the formula that we'll be using, and by this I can say work, all right, when we have two things. Let's say I'm trying to just find the integral, still the same thing, I'm still negative the integral of, let's say we have two volumes, so volume 2 I'll put it there, which is just a definite integral. I'm just representing this in the way I want. So I'll have v prime there, all right, then we are saying This is the pressure what? External, right? Then there will be dV like that, change in volume. So this pressure here, I can what? I can so that pressure there, I can what? I can is constant, all right? So the pressure is constant. What I can do is negative. Um I'll say work is equal to negative. This pressure is external, right? The integral of what? Change in what? In those volume that I have minus the initial. Then change in what? Volume. This is the meaning there. It's just the interpretation. Don't get confused of this integral. Okay, hope that is clear. So what you're going to do here is that we'll leave it like that, okay, as the formula for work. So from there, then what we can say is that to conclude, to say work is equal to what? Negative, all right? Um, Pressure external, then times change in volume, all right? So volume 1 minus volume 2, okay? So that is it. That's what we'll be doing, all right? So just know that when we have this one, once this one is greater than, then we'll have negative work. Once this one is less than, then we'll have what? Positive work. Meaning that when it's positive, just know that the work was done on a system. But when work is negative, just know that the system was doing work. Okay, so let me give you an example. Example question, how exam can uh, given from this. So suppose we have the volume increased from 10, all right, decimeter cubed to what? To 20 decimeter cubed. Then at what? Let's say at 2 atm. All right. Calculate the weight of what? External pressure. Okay. Of external, because the external pressure is the one in charge of, let's say, balloon, is the one causing this balloon to compress or just to expand when it reduce. All right, it will allow the balloon to what? So say work is equal to what? Negative pressure, all right, external, okay, change in what? Let's say volume 1, volume 2, then volume 1 there, okay, d what? Volume. Then what I'm going to do is I'll have negative, what is my pressure? External pressure there is 2 atm. So I'll say 2 atm, all right. Then open bracket. The change in volume now is 20 minus 10, then decimeter cubed, like that. So what we are going to do is um, we'll say we'll multiply there. So it is what? Negative 2 atm times, this is what? 10 decimeter cubed. Okay, so from there we need to know that, and we are calculating this work in joules. Remember, calculate the work of external pressure in what? In joules. So we have this work now. So what you are going to, this work is now measured in what? Negative, I can now say negative 20 atm. So this liter or decimeter is equals to a liter, so I'll say liter. Okay, and I know that um I know that 1 atm liter is equal to um 10 1.3 joules, like that. So I'll just replace wherever there's 1 atm liter or just atm liter, I'll replace with that value. So what I'm going to do is I'll say negative 20, all right, then I'll put my relationship there, which is 101.3, okay, joules, like that. Then from there I'll be able to multiply and also get my work there. Okay, so that is it about this. So in the next video, that's where we'll be actually doing some things involving work conversions, everything like that. So make sure that you watch out the other videos. Otherwise, thank you very much. Um, Thank you very much for watching the video.